This video is for section 7-5, Properties of Radicals. Let's begin with this theorem, the product property of radicals theorem. If n is a positive integer and all of these expressions are real numbers, then this is true. The nth root of a product is equal to the product of nth roots. You can kind of think of this as factoring, rewriting this product as the two factors that multiply together to create it. With that theorem, we can simplify expressions involving radicals. Let's say we wanted to find the square root of 242y cubed. We can rewrite that as a product of square roots. For example, 242 is equal to 121 times 2. And y to the third power is equal to y squared times y. Now you might be wondering, why would you write it like that? The reason is that in the first radical are perfect squares. The square root of 121 makes 11, and the square root of y squared makes y. The other radical does not have perfect squares inside of it, and so you would leave that piece in a radical symbol. The square root of 242y cubed can be rewritten as 11y times the square root of 2y. Let's try another one that involves a cube root. To find the cube root of this expression, we can rewrite it as a product of cube roots. Now let's think about what factors to write in the first radical and what factors to write in the second radical. In the first radical, we want to have only perfect cube numbers so that when you find the cube root, you get whole numbers. 64 is a perfect cube already, so let's leave 64 in there. X to the first power, however, is not a perfect cube. Let's put the x factor in that radical. Y to the sixth power is a perfect cube, so we'll leave it in the first radical. One more step. Find the cube root of every factor written in the first radical. The cube root of 64 is 4, and the cube root of y to the sixth power is y squared. Leave the other radical in radical notation. Here's another theorem. If m and n are positive integers and b and the nth root of b are real numbers, then this statement is true. Finding a root of a power is equivalent to finding the power of the root. Let's try some examples of that. To find the fourth root of 16 to the third power, we could rewrite this as the fourth root of 16 raised to the third power. The fourth root of 16 is 2, and 2 raised to the third power makes 8. Next example, to find the cube root of a number to the second power, we could find the cube root of the number and then raise that to the second power. The cube root of negative 27 is negative 3, and then when you raise that to the second power, you get the answer 9. Another theorem, the quotient property of radicals. If n is a positive integer and all of these expressions are real numbers, then this statement is true. The root of a quotient is equal to the quotient of roots. This is related to the product property, where you could separate a product into two pieces. Here we're separating the quotient into two pieces. Here are some examples of that. Let's say we wanted to find the square root of the quotient y to the 8th divided by 32,400. We could rewrite this as the square root of y to the 8th power divided by the square root of the 32,400. The square root of y to the 8th power is y to the 4th power. And with the help of a calculator, the square root of the denominator is 180. Next example. This one uses the converse of the theorem. Instead of having a square root in the numerator and another square root in the denominator, we could rewrite this using a single square root symbol and form a quotient from the radicands. Then simplify that fraction that's in the square root. 98 divided by 2 is 49, and t to the third power divided by a single t is t to the second power. These are both perfect squares in the square root, so the final answer is 7t. The theorems enable us to simplify terms involving radicals with index n. Terms with radicals are in simplest form when the following criteria are met. So you know in algebra, we're always trying to put our answers in simplest form, but sometimes it's unclear what that means. How do you know how far to take an answer so that you get it to what mathematicians call simplest form? In the case of radicals, these are the 4 rules to follow. No radicand that's an integer can have a factor that is the nth power of any integer other than 1. That sentence is a little confusing, but we applied it in the last example that we did. I knew that this was not simplified because 49 is the same thing as the integer 7 to the second power. And that power matches the index of a square root, which is always a 2. Second criterion, no polynomial radicand can have a factor that is the nth power of any polynomial other than 1. That rule came into play with the variable piece. I knew that this wasn't simplified yet because the variable's power of 2 matches the index of 2. You can actually find the square root of t to the second power. It makes t. The third criterion is that there can be no fractions or powers with negative exponents under the radical sign. That was the rule that we applied for this example. There's a fraction under the radical sign, so this was not simplified. The fourth rule is that no radical can be in the denominator. And that rule applied to that very last example. Because there is a radical in the denominator of this expression, it was not simplified. If you're expected to simplify an expression that has a radical, these are the 4 rules to run through to determine if you have simplified the expression. Make sure that there are no radicals in a denominator. Make sure that there are no fractions under a radical. Make sure that no variable terms have a power that you could take the root of that power. And make sure that no numbers in the radicand can be factored in a way that you could take the root of one of those factors. One of the rules is that there can be no radical in the denominator. To accommodate that last criterion, you can use a process called rationalizing the denominator. For example, let's say we want to simplify 6 divided by the square root of 2. This has a radical in the denominator, which means it's not simplified. How do we correct that? Rationalizing the denominator is the process of multiplying the top and bottom of the fraction by the denominator. Because you're multiplying top and bottom by the same thing, you're not changing the overall value of the fraction. Then write down what this creates. In the top, we have 6 times the square root of 2. In the bottom, the square root of 2 times the square root of 2 is equivalent to the square root of 4. But that just makes 2. Then we can simplify the whole numbers 6 over 2. Final answer is 3 square root of 2. Next example. We have the cube root of this expression. This is not simplified because it has a fraction, but also because it has a negative exponent in the radical. First step, let's rewrite that and correct the negative exponent. This is equivalent to 1 over 200 r to the 4th power. Next step, let's apply the quotient property and rewrite this as the cube root of 1 divided by the cube root of 200 r to the 4th. The cube root of 1 is just equal to 1. So we could rewrite this as 1 over the cube root of 200r to the 4th. But we're not done because there is a radical in the denominator of a fraction. So let's rationalize the denominator. To turn the denominator into a rational number, we need to have things inside the radical that we can take the cube root of and get nice results, not decimals. So the process of rationalizing is to multiply the top and bottom by the same thing. The kind of radical we have down here is a cube root. So let's figure out what cube root to times in the top and the bottom. Remember what our goal is. We want to create something inside the radical that when you take the cube root of it, you get an integer, not a decimal. Well, the cube root of 200 is a decimal, but what could we turn 200 into so that it's a perfect cube? The one that comes to my mind is the number 1000. The cube root of 1000 is just a 10. So to change 200 into 1000, we'd want to times by a 5 inside of our root and in the top. Now let's also think about the variable r. Right now, the cube root of r to the 4th power doesn't work out nicely because this power is not a multiple of this index of 3. Well, what could we turn r to the 4th power into so that we can take the cube root of it and get a nice result? The one that occurs to me is r to the 6th power, because if we had r to the 6th power, then we could find the cube root. Well, if I want to make this have r to the 6th, I need to have an r squared in my radical, because r to the 4th times an r squared would be r to the 6th, and in the top. So what I'm showing here is a process called rationalizing the denominator, deciding what to times by so that the denominator will turn out to be a nice result, not a radical symbol. So next step, in the top, we have 1 times this radical. That's going to make the cube root of 5r squared. And in the denominator, when we times these radicals together, we have the cube root of 1000 r to the 6th power. That's equal to the cube root of 5r squared in the top, and in the bottom, 10r squared. So we no longer have a radical in the bottom. We have rationalized our denominator. Here's the final answer. Let's summarize this lesson. We reviewed simplifying radicals. To simplify a radical, you want to make sure that your answer follows some requirements. And those requirements were given in this lesson. If we back up just a little bit, you can see the 4 requirements that you have to follow to simplify radicals. We don't want to have any radicals in the denominator. We don't want to have fractions in a radical. And when we have variables or numbers in the radicand, we might need to use factoring so that we can take the root of at least part of the number that's in there.